Welcome to our lecture online, and in this video we're going to take a closer look at the Carnot cycle, which is based upon the theoretical Carnot engine, the engine that Carnot, which is a famous physicist, devised from a thermodynamic process. This is of course not a real engine and not an engine you're going to go down to the shop and build yourself, but an engine that's based on a theoretical model that exists as follows. We have a thermodynamic process that goes from A to B to C to D and back to A. From A to B, we go along the isotherms, that's an isothermic process. From B to C, that's an adiabatic process. From C to D, that's again an isothermic process. And from D back to A, that is an adiabatic process. And Carnot showed and proved that this is the most efficient engine you can have. All other engines you can devise, any other thermodynamic process, will have an efficiency lower than the efficiency of this particular engine. Remember the equation for efficiency. Efficiency is equal to work done divided by the heat that you derive from the hot reservoir. And work done can be written as Q hot minus Q cold divided by Q hot. And if you divide this into that, you get 1 minus Q cold divided by Q hot. So what we want to do here is come up with an equation where we're going to divide Q cold by Q hot somewhere in this process. Now remember that in an isothermic process, based upon the first law of thermodynamics, delta U is 0, and therefore Q equals W, which is equal to nRT times the natural log of V final over V initial. So if we're going to use that, let's start with Q cold, the heat expelled at the cold reservoir. Q cold is equal to nR times the temperature cold, because at that point the temperature is T cold, times the natural log of V final over V initial. So in this part of the cycle, in this process, V final is VB and V initial is VA, so we write VB divided by VA. Now, to find the heat being put into the system or into the cycle at the hot temperature, we have QH, and that is equal to nR times temperature H times the natural log, and again, that would be V final over V initial, so it would be VD over VC. Now, there's a mathematical trick here. We're going to take the negative of this. In other words, if I put a negative sign in front of that and I exchange VC and VD, then that makes that negative as well, and they cancel each other out. So I can write QH is equal to the negative of nRTH times the natural log of VC over VD. Remember, when you interchange those two variables, that becomes negative, and that's then negated by the negative over here. And again, there's a reason why we did that, because the next step, we're going to divide Q cold by QH to get that right there. So Q cold divided by QH can now be written as this right here, which is nRT cold times the natural log of VB over VA, that's this right here, divided by the negative of nRTH times the natural log of VC over VD. And then right away you can see that the N and R cancel out, and now we have TC over TH and the natural log of VB over VA times the natural log of VC over VD. So that's equal to Q cold over Q hot, which is the part of our efficiency equation we have over there. So the next thing we're going to do is look at the adiabatic part of the cycle right here, the two adiabatic processes, and use this equation to relate temperature to volume as well. And then we should be able to solve those two equations simultaneously. So starting with going from B to C, we can write temperature at B, and of course temperature at B is T cold, times V at B, and V at B, well, that's simply V at B to the gamma minus 1 equals temperature at C, which is T hot, times V at C to the gamma minus 1. We can also do that for the other process right here, going from D back to A. So we can say T at D, and of course T at D, that would be T hot. So T hot times V at D to the gamma minus 1 is equal to, when we get over here, that would be T cold times V sub A to the gamma minus 1. So we used that equation to relate B and C and D and A, because that's an adiabatic process and that's an adiabatic process. Now, what I need to do is I need to somehow get rid of the Tc and Th here. All right, so how do we do that? How do we get rid of the temperatures in these equations right here? Well, if I divide this equation by this one but turned around, then I have Tc's lined up, I have Th's lined up, and then I think those will drop out. So let's try that. So we're going to take Tc Vb to the gamma minus 1 and set equal to Th times Vc to the gamma minus 1. And we divide that by this equation, but turned around, I get Tc Va to the gamma minus 1. And on this side, I get Th times Vd to the gamma minus 1. Notice what we've done here. You can see that the Tc's cancel out and the Th's cancel out. And then you combine the Vb over Va and Vc over Vd. So we can write that Vb over Va to the gamma minus 1 equals Vc divided by Vd to the gamma minus 1. Now, why did I do that? Well, take a look at this equation again. I have Vb over Va, and I have Vc over Vd, which is exactly what I have over here. And you could say here then that if Vb over Va to the gamma minus 1 equals Vc over Vd to the gamma minus 1, that these ratios have to be equal to each other. If those two ratios have to be equal to each other, then this has to be equal to that, and those cancel out. Because Vb over Va is equal to Vc over Vd, which I have over here. And then I look at this equation, I can write that Qc over Qh is equal to Tc over Th. Of course, don't forget the minus over there. Now, does the minus make sense? Well, it depends. Notice that if I only take the absolute value of the left side, excuse me, of that equation, because if I simply look at the quantity, not the sign, and if I then write it like this, if I say the absolute value of Q cold over QH is equal to, and I can just get rid of this negative sign right here, and simply say that is equal to T cold over TH as a positive quantity. And then I can see over here if the efficiency is equal to 1 minus Q cold over QH, and I have determined that Q cold over QH is equal to C cold over TH, T cold over T hot, then this equation then becomes the efficiency is equal to 1 minus T cold over T hot for a theoretical Carnot engine. And that then is the maximum efficiency any engine can have, simply 1 minus T cold over T hot. Now, of course, that can be written in a couple different ways, but also can be written as E is equal to, just like we did there, T hot minus T cold divided by T hot. And that's another way of writing the maximum efficiency of a Carnot engine. So that was pretty neat that Carnot came up with this concept that there's no engine with any greater efficiency than this engine right here. Of course, not a real engine, theoretical engine, but at least for engineers, they know that they can never exceed this. And if they want to make an engine more efficient, they can do that by making this relationship as small as possible, meaning make T cold as small as possible and make T hot as big as possible. They get the greatest maximum efficiency an engine can produce.